As some of you may know, my group has been working in statistical genetics for a few years now, and it would be natural to give a talk that would be a continuation of Jennifer's talk in terms of the topics. But then I remember that I'm really, before I'm a statistical geneticist, I'm a statistician. And I felt it would be interesting to talk to this audience about something that I feel some of you may find interesting and useful. So I'm going to be talking about Bootstrap. So I'm sure everyone here has heard of Bootstrap, and many of you have probably used Bootstrap over the years. But perhaps in many cases, people think of Bootstrap as an algorithm or a recipe. And I want to take a step back and think of it more fundamentally. So the point of view we're going to take is that Bootstrap is a paradigm and not an algorithm. And now, of course, the question becomes, what's a paradigm? Luckily, some great thinkers have addressed this question of what's a paradigm. So, paradigmism, as in this Bootstrap is a paradigm. So that's a paradigm, okay? So let's think abstract about what is statistics. So in general, for a statistician, there's a world, and because we're a statistician, the world is actually a distribution, right? So the world is represented by some distribution that is typically unknown to us. And then we observe some data from the world, and running example that we're going to be using is, say, we observe 100 pairs of heights and weights of some random people. Okay, so this is our view of the world, but we know that there's a distribution out there. Okay, and then what do we do as statisticians? We take the data we see and we use it to try to estimate things about the world, about the unknown world, right? So what kind of things would we want to estimate in our running example? So obviously we may want to know what the average height is in the population. So these are properties of the world, right, that we would like to know about. For example, what's the average height in the world? Or we may want to know what's the correlation between height and weight in the world, right? Or we may want to know some more complicated things, such as, say that we take the empirical correlation between height and weight from our data, what's the variance of this quantity? And why would we be interested in such properties? Because if we know what the variance of our estimate is, then we can not only use our estimate to estimate the correlation in the world, we also have an idea of how accurate it is. Right? If its variance is small, then it's an accurate estimate of the true correlation in the world. If the variance is big, it may not be an accurate estimate. Right? But I want to emphasize that this variance is actually a property of f. Right? When we ask about the variance, we are actually imagining that we take f and we draw many samples of size 100 of it, and we look at all the correlations, and we see what the variance of these correlations is. Right? So that's also a property of the world that we may be interested in. Okay, so this is our task. We have a world, we see a sample, and we want to estimate properties of the world and then do some things with our estimate. And what do we learn in Stats 101 about how to do these things? So basically, we're told you're given this data, and now find a way to estimate what you want from this data. Find some calculation and ask yourself about the properties of your calculation for estimating the property of the world, right? So, for example, if we wanted to estimate the mean height in the world, obviously, we would take the average, and then in Stats 101, we learn many reasons why that's actually a good idea, not just an intuitive idea to take the average of the heights in the sample as an estimate of the mean height in the world, right? So if we wanted to estimate the correlation between height and weight in the world, then naturally, we would take the empirical correlation from our 100 size sample. Now, the question becomes, what do we do if we actually want to estimate the variance of this empirical correlation estimate, right? So that's slightly more complicated, typically not something we learn to do in Stats 101, how to estimate this variance of some complicated estimate in itself, which the correlation is not very complicated, but it's more complicated than the averages we usually calculate in Stats 101. So what do we do if we want to do that? So we can find some complicated formulas that give us reasonable estimates of this quantity under some assumptions. But it gets a bit complicated for this quantity already, and we may want to estimate much more complicated things that we can't figure out a formula for. or an estimator with good properties. So we're going to try to think about this differently. We want to think of a general approach that will basically allow us to estimate every property of f and is not going to require doing complicated math or complicated probability. Okay? So I have a world, I have data. I want to learn anything about the world. I want a general approach that will allow me to do that. Okay? While not remembering any of the complicated math I might have learned as an undergraduate. So that's one way to think about what Bootstrap is. And Bootstrap is really, the main idea is actually what's called the plugin principle. And if we understand the plugin principle, then we understand the Bootstrap paradigm, even if we don't know what a paradigm is. So really, the key is understanding what the Bootstrap principle is, what the plugin principle is telling us. So the plugin principle is telling us we are interested in some property of the world, right? So this is some just vague notation. There's a world. We want to apply some function to it, t, and then that gives us the property we are interested in. Okay, so it just says that the property we're interested in is a property of the world. That's all it says. And the plugin principle is we're going to go back to childhood, and we're going to invent a new world that we're going to call f hat. Okay, we're going to figure out a way to invent a new world that's going to be known to us. The world we invent is going to be a world where we know the actual distribution of the world. Okay, and then in this world, we're actually going to empirically find out what the value of the property is in our toy world, in our Bootstrap world. Okay, so one way to define a world that we know is to take the empirical distribution of the data. Okay, we have 100 samples, so we imagine a world where only 100 different objects can exist, the 100 objects that we observe, and that's the world that we're going to be doing our Bootstrap in, and that's going to lead us to the standard Bootstrap recipe that many people know as Bootstrap. Okay, and we're going to show how that happens. But there's many other ways that could be thought of to define worlds that define Bootstrap worlds and do the plugin estimation in the Bootstrap world. Okay, so really the question is, this idea is very general. I think actually it's an easy, simple idea that makes a lot of sense. But really the question is, how do we define a Bootstrap world that is going to be useful for our purpose, right? We can take any distribution we want and call it our Bootstrap world, but we have to be smart about it. And what does it mean to be smart about it? It means that it has to be similar to the real world we don't know, but it has to be similar to the world in the ways that matter to us. And what are the ways that matter to us? That the quantity theta hat that we estimate in the Bootstrap world is actually going to be similar to the quantity theta that we want in the real world. Right? So that's still abstract, but that's really what we should aspire to. So the main question is, how do we define a Bootstrap world that's going to be appropriate for our task? A secondary problem is how do we actually perform the estimation in the Bootstrap world? And as I'll show you, this is usually a very straightforward exercise to do the estimation in the Bootstrap world once we have it. Okay, so we can draw a graphical. There's this very famous graphical representation, my version of it. This is what we have in the real world. We had some distribution f. We have some data coming out of the distribution. We do some estimation with our data. Say we estimate the empirical correlation. And in the cases that we're interested in, there's some property of the world that we want to estimate. And the property is usually related to our statistic. So in our example, the statistic is the empirical correlation. And the property of the world is the variance of the empirical correlation that we want to estimate. Okay, so this is the picture we're faced with if all we did is 101, and we may be quite helpless in how do we use our data for estimating our quantity of interest. So the idea of Bootstrap is now we invent this Bootstrap world f hat, and within the Bootstrap world, we know the distribution, so we can draw data using the same. So this is IID drawing of 100 pairs. We can draw IID 100 pairs here, calculate the value of the statistic, and then we can repeat this exercise not as many times as we want, right? Because we know the distribution in the Bootstrap world, so we can draw many samples of size 100, and for each one of them, we can estimate the empirical distribution. So if we now don't have one empirical distribution, but we have 1,000 empirical correlations, we have 1,000 empirical correlations, then we can just empirically estimate what the variance of the empirical correlation is. Okay, so that shows us an example of why it's actually easy to estimate things once we're in the bootstrap world. Okay, so you may tell me, okay, this is some statisticians came up with this crazy idea of inventing a new world. So the question, of course, becomes, is this important in practice? And it may not be necessary to convince this audience, but just to make sure, you know, there's several versions of reality TV shows for scientists, right? One has to do with where you published. A more advanced one maybe has to do with how many times the work is cited. So this is the reality show of citations, and these two basically an introduction to the bootstrap, which is very nice presentations of some of the ideas I'm talking about, and this famous paper by Felsenstein applying the bootstrap to phylogenies, which I've seen several examples of use in this conference already. Both of them have over 30,000 citations, each one of them. So that's just to emphasize the point that this is very important, very widely used idea, and I think it's important that we understand sort of the fundamental thinking about bootstrap. Okay, so let's make it more concrete and take our example and run through it. And our example is to estimate the variance of the empirical correlation in our 100 size sample. Okay, so in the world we're interested in is actually a bivariate distribution of heights and weights. And the data we're given is 100 pairs of heights and weights. We assume drawn IID from this world. And the statistic that we are thinking about is the empirical correlation. But actually the property we're interested in is this variance in the real world of this statistic we calculated, right? So that's basically asking how stable is the empirical correlation as a measure of the true correlation between height and weight, right? So what would the bootstrap approach for this look like? The bootstrap approach would call to build the bootstrap world that we're going to call f hat, repeatedly draw, bootstrap samples of size 100 from this world, repeatedly estimate the empirical correlation for each one of the size 100 samples we drew, and then use these estimates, for example, to empirically estimate the variance in the bootstrap world of the empirical correlation. And now we have a bootstrap estimate of the variance of the empirical correlation, right? So basically we're done. And this general recipe, there's basically only one thing that we need to determine here. How do we build the bootstrap world, right? And what kind of bootstrap world do we build so we get actually a good estimate of what we're trying to estimate? So that's really the key question, basically for any bootstrap exercise. How do we build the bootstrap world? Okay, that's the double arrow in that graph that I showed, in that schematic that I showed. And the most standard approach, or what's often just called the bootstrap, is to use the empirical distribution of the data. What does it mean in our case? In our case, it means that we take a bootstrap world where there's only 100 possible values, each of them with probability 1/100. And now we draw a random sample from that world, which basically amounts to doing bootstrap sampling from our original data set, random sampling with return, right? So that's random sampling, that's IID sampling in a world where we only have our data and nothing else. Okay, so if we make the world the empirical distribution of our data, we usually end up with standard bootstrap, which is in more carefully what we would call non-parametric bootstrap, because it assumes actually nothing about f. It assumes nothing except that our original sample is a random sample from the world f, right? But one important message that I want to make sure sinks here is that this is not the only approach, and it's often not the best one to build a bootstrap world. Okay? So let's think about a different way of handling this problem. And the different way I'm going to be describing here is what's called parametric bootstrap. And for that, we may want to assume that we know something about f. For example, so before we assumed we know nothing about the world distribution, let's now venture to assume that it's a bivariate normal distribution. Okay, so height and weight are jointly normally distributed. We're going to add this assumption. In that case, it may make sense to try and make f hat also a bivariate normal distribution, right? And if we want to use a bivariate normal distribution whose parameters we know, where should we bring these parameters from? It makes sense to try and estimate the parameters of the bootstrap world from the data, right? So there's this very standard problem of estimating the parameters of a bivariate distribution from a sample. So we just take the estimates from the sample and use those to build our bootstrap world, right? And now the recipe is exactly the same as what we saw here, right? The recipe is the only thing that changes how we build our bootstrap world. Now our sampling is no longer a bootstrap sampling. It's no longer what's often called bootstrap sampling. It's a different way of sampling, but it follows our general plugin principle. Okay, so let's make this concrete. And let's get some data. So now being the almighty simulator, I can build a world F actually. And in my world F, this is binormal with means 175 and 75. And this covariance matrix for height and weight. Okay, this is in centimeters and kilos. So, for example, I want to know what the variance of the empirical correlation is. Then in my simulation, I can just draw many samples and just empirically see what the actual variance of the empirical correlation is. So now I know that this is the true value of my parameter of interest in this world. Okay, almost exactly the true value I'm interested in. I haven't done any bootstrap yet. I've just done simulation to find out what the actual true value of my parameter is. Okay, now I want to compare the different bootstrap recipes for estimating this parameter, this quantity, using the bootstrap recipe. And basically, we've discussed two bootstrap approaches for this, so let's try both of them. So the first one is the standard non-parametric approach, where I define f hat to be the empirical distribution of my sample, right? And so I just do bootstrap sampling. Every time I look at the empirical correlation in my bootstrap sample, and then I estimate the variance of S by just the empirical variance of S hat over many bootstrap repetitions, right? So that's a standard non-parametric bootstrap. And because I'm simulating, I can actually draw many different x's. For each one of them, see what the bootstrap estimates comes out to be, and get a distribution of bootstrap estimates for this approach, right? See, in general, how accurate are these bootstrap estimates compared to the true value I'm interested in of the variance, right? And then I can do the same thing with the parametric bootstrap. What would that entail? Every time I get x, I use it to estimate the mean and variance and covariance matrix of the binormal distribution. And then f hat is this normal distribution with this mean and covariance matrix. And the rest is exactly the same. I sample x stars from this binormal distribution, right? Just using a standard random sampling approach from a known distribution. I estimate the empirical correlation. And then I look at the variance of S, and I estimate it by the empirical variance of this S star over the bootstrap repetitions. And so a question we may ask ourselves is, which approach is expected to be better for this specific world that I built? And the property of the world is that it is actually binormal distribution, right? Yes, Jen?
Do people ever combine the two?
How would you combine them? I mean,
in the parametric, you're fitting the data to the model to get the parameters, and then you generate sort of infinite data.
Mm-hmm.
But so that's subject to, like, you don't know the variance of that original estimate of the model parameters. So you can imagine sort of two levels, right?
Oh, there's two-level, three-level bootstraps. Okay. There's all kinds of multi-level designs that I don't think we're going to be discussing.
So people do that?
Yes, of course, yes. Maybe for slightly different purposes, but we can take that offline. So which one is expected to be better here? Obviously, I think it would be obvious to everyone, because the true world is bivariate normal. I would expect to see that for my example here, hopefully the parametric bootstrap is going to be better than the non-parametric bootstrap, right? So here's the results of repeating this exercise many times. So I get actually a distribution of estimates from the non-parametric and the parametric bootstrap. Remember, the true value of my parameter is 0.00261. So I get means that are very close. But in terms of standard deviation, I get much smaller standard deviation for the parametric bootstrap estimate compared to the non-parametric bootstrap estimate. And that's also actually a standard thing you often see. That when you do parametric bootstrap, you get a smaller variance than when you do non-parametric bootstrap. But in this case, because the parametric assumption is also correct, in general, I got a better estimate using the parametric bootstrap than using the non-parametric bootstrap. Okay, so this completes our run through our example and applying two different approaches. And so we have this sort of what I called magic wand in the beginning. Does it always work? And the answer, unfortunately, is that it does not always work. And the reason it doesn't work is what I'm emphasizing all the time, is that this is really an assumption, or if you want, a wish, that we can build a bootstrap world such that the value of the parameter in the bootstrap world is actually similar to the value of the parameter in the real world, right? And this is, we may build a bad bootstrap world in the case that this is possible, or there are some examples where this is just impossible. We can prove and demonstrate that there are some quantities of the real world that the assumptions to estimate them with bootstrap are going to be doomed. Again, this can be because we built a bad bootstrap world. For example, if we assumed bivariate normal, then built a bivariate normal bootstrap world, but the true distribution is very far from being bivariate normal, that's likely to lead us to bad bootstrap estimates. And as I said, it's also easy to devise examples where actually no bootstrap approach would give reasonable results. Examples of problems where no bootstrap will give a reasonable result. Of course, if I know the real world, then I can build a bootstrap world which is the real world, and then I will always get good results. But based on data, we can give examples. But I think that it's easy to see by looking at Google Scholar or any other place that the usefulness of Bootstrap is very general, and it applies to many, many important problems we encounter that we may not be able to solve and estimate things if we did not have this very powerful tool. Okay, so I really want to get into a very interesting and slightly maybe more complicated aspect, which is how to do hypothesis testing with Bootstrap. Okay, so as we've heard already, what's a hypothesis testing problem? A hypothesis testing problem has some null hypothesis, which is an assumption about basically the world, that the value of some parameter is some value in the world, and then a test statistic, which is supposed to be related, supposed to carry information about the value of the parameter. And what's a hypothesis test is basically calculating a probability under, if the null holds, of getting some value of the test statistic or more extreme, right? So we observe the value z, and we want to calculate the probability of being beyond z. And if that probability is very small, then something has occurred that is very surprising given our null assumption, and we feel comfortable rejecting the null hypothesis, right? So the point is that this, what's written here, if we observe some value of the test statistic, let's fix the value of the test statistic, this thing is actually a property of the world, right? If the null assumption holds, if the null hypothesis holds, then this is some property of the distribution under the null hypothesis, right? So fixing the value of the test statistic, this is a property of the world we want to estimate, but can we use the Bootstrap to estimate it? So here, a very simple case is the fact that H0 actually defines the distribution exactly of the world, what's called a simple null hypothesis, right? If we have a simple null hypothesis, then if the null hypothesis holds, I know the distribution, and then calculating a probability under the distribution, we can think of it as a Bootstrap exercise, or we can think of it as just drawing data from this non-distribution and seeing how often it falls above the value we observed in the data, right? So in that sense, if we have a simple null, and we're drawing samples from it and seeing if they are more extreme or less extreme than our observed value, we are doing Bootstrap. We are doing a plug-in estimate of the p-value. And this is what we often do. It gets much more interesting if H0 does not define the probability uniquely, right? So the case that H0 contains many possible distributions. And we can still implement the Bootstrap paradigm. And the way remember, the bootstrap calls for estimating a probability under the null, right? So the proper way of doing that is we want to choose f hat as the member of the null that is most consistent with our data, that's going to give us the most conservative p-value out of all possible worlds in the null, right? Because, so a way of, I wrote here this probability under the null, but actually in the case of complex null, the way we define it, it's actually the maximum of the probabilities under all possible null models. So this is a bootstrap way of capturing that, right? We need to define a bootstrap world that's going to give us an idea of the maximum possible probability under the null. Okay. So here's a very interesting example, and I think it's interesting, but at least 30,000 people have cited it as being interesting. This is Felsenstein's famous paper on how to do inference on phylogenetic trees. And here's some data actually from his original paper. These are malaria sequences of malaria pathogens from different hosts, right? And the length of the sequence is 221, and we have here just 20 characters from the sequences. And what they did, or maybe it was done before, was build a phylogenetic tree based on these samples. This is the phylogenetic tree that came out. And the question that Felsenstein chose as an example, or we're going to concentrate on, is a question about this clade in the phylogenetic tree. This is a clade of these two parasites, one whose host is monkey and one is human. And the question is, are we confident that this is actually a clade in the true world, right? The true world, actually those malaria parasites have some history, and some of them have some true phylogeny. And the question we want to answer is this clade that we got in our empirically estimated phylogeny from the data, is it actually a clade in the real world, in the history of malaria, right? So let's talk about what Felsenstein did. So Felsenstein had this phylogenetic tree built on this data set, and he wanted to ask whether this clade 910 is real. So that's like asking, does it exist in the world and not just in the phylogenetic tree we built on our data, right? So it's really a question about our confidence in the results from building the phylogenetic tree. And his bootstrap worked like this. He draws bootstrap samples of markers. These are columns of our matrix, right? So basically his F is a uniform distribution over the observed columns of the matrix, and he draws a bootstrap sample in that world, so that entails drawing columns of this 221 columns with return from the original matrix. He built a tree on each one of these, and this tree used all species and the sampled markers. And he used the percent of the time that the subtree T0 came out in this bootstrap exercise. This is our confidence, right? This is this 96.5, and the number we've seen on phylogenetic trees several times in this meeting. This is how they're generated. And the question that I want us to ask is to think critically about this exercise and the stated goal, and ask ourselves whether this actually attains the stated goal, or is it a good way of attaining this stated goal. Okay, so we want to know whether the subtree exists in F, right? And we estimate this by the percentage of the time that the subtree exists in the data that was drawn from our F hat, from our bootstrap world, right? And we can spend some time explaining why this may not actually be a plug-in recipe for answering this question, but it's not critical. So let's assume it's a good plug-in way of estimating this quantity we're interested in, which is whether or not the subtree is in F. The question is it a good one? And I think it's problematic, and not only me, we'll see some other people who think it's problematic in a little while, because F hat was built based on this sample, where in this sample, the phylogenetic tree that came out actually contained this subtree. Okay, so we built a world where in some sense we already know that this subtree exists in this world because it existed in the phylogenetic tree we built from the entire sample. So in some sense, we think that this is likely to give us over-optimistic results in compared to the true notion of what confidence in subtrees should mean. And then we can ask ourselves, what's a good way of getting maybe a good measure of confidence in subtrees? And I think it's pretty natural to think that this may be appropriate to approach it as a hypothesis test. So a hypothesis test meaning we have a null hypothesis that we believe in unless convinced otherwise, right? So let's choose the null hypothesis that this subtree, T0, is actually not part of the true T tree in the world. So this is going to be our null hypothesis, the conservative view that now you have to convince me that this tree actually does exist. This subtree actually does exist in the tree. So if we reject H0, then we can conclude that this subtree T0 is reliable, right? So what I'm going to do now is concentrate on another very well-known, less well-known, but also well-known paper by Brad Efron and collaborators that addressed this point of view that I just presented to you, that we should be building a bootstrap world where we should be treating this as a hypothesis testing problem, meaning we should be building a bootstrap world that is as similar as possible to our data, but where the null holds, right? And then we should be using that to calculate p-values for our sample. And for our null, the T0 is not a subtree. OK, so this is a paper in '96 in PNAS. And they have some complicated Bayesian setup that explains how we can view the approach as a legitimate bootstrap. But again, being a legitimate bootstrap or legitimate plugin exercise does not yet mean that it's a good way of doing bootstrap, because it's all about how we build the bootstrap world, right? But they show that without this thinking, we can think about this as hypothesis testing and basically get a bootstrap that treats it as a hypothesis test, where the null is that the subtree is not part of the tree. Now, the math and geometry that this entails actually gets very complicated. OK, but I have a few details about it. So our task is to build a bootstrap world where H0 holds, which is easy, which is relatively easy. We just need a bunch of data where we estimate the phylogenetic tree, and we don't get H0. We don't get T0 subtree. But we also want to make this bootstrap world as similar as possible to the empirical distribution of our data, right? This is the key task here that makes it complicated. How do we find a world where T0 is not a subtree, but it is as similar as possible to our empirical data? Once we do that, it's easy. We can test H0 by just drawing a bunch of samples from this bootstrap world and then seeing what percentage of time T0 gets selected in this world, right? Now, if in data drawn in this world, and if this percentage is smaller than 5%, then basically we reject H0 at the level we said, and we conclude that T0 is well supported by our data, right? Or we could use 1 minus this as a confidence measure, same as the numbers currently given. And the challenge is, of course, this first task. So first of all, we have to say what it means that H0 holds in some world, and that's defined. Efron defines that by multivariate distributions over possible columns. It's a bit complicated, and we're not going to get into this, but I have some nice graphical representations of the ideas in the book. So basically, he's saying, let's take the region R1 as distributions over columns where T0 holds. OK, so in a place where T0 is a subtree, what do the distributions over possible columns of the matrix look like? And the other regions are regions where T0 don't hold. So basically, we divide the space of distributions over columns to regions according to the true phylogenetic tree implied by each one of these possible distributions over columns of our matrix, over sequences. And R1 is the one where 9, 10 is a subclade. And the others have different topologies that don't contain 9, 10 as a subclade. Okay? And basically, and here is our empirical distribution in our data. We know that it lies in the R1 region because we got the 910 clade in the original sample. And here we have the true distribution. In this case, it actually is also in the R1 region. So this is a case where the null doesn't hold. And here is some distribution. Here is some bootstrap world that complies with our null because it's not in the R1 region. It's in a different region, right? So basically, our task is to find a point on the boundary between R1 and the different regions that is as close as possible to our empirical distribution. And that's going to be our chosen bootstrap world. So basically, the paper is concentrated around how you solve problems like this. This is an illustration of this idea on a much simpler problem of estimating normal means. Maybe I'll say one word about it. Think about, it illustrates two different cases, the one on the left versus the one on the right. The one on the left is a case where the boundary between the null and non-null is this straight line, and we have normal distributions. In this case, what Efron is saying, if I take my, so on the left we have null, on the right we have non-null. Efron is saying and this is my data, right? So in this case, if I take a normal distribution around my data and I calculate the Felsenstein quantity, it's the probability of falling beyond the line, right? Because it's a percentage of the time that I don't get the clade in my sample. If I take the Efron approach, it's finding the closest point within the region, which is this point here, and then drawing normal samples around this and calculating the probability that they fall beyond the observed value. Okay? And he's saying if the line is a straight line, these two ways actually give the same result. If the space has a more complicated geometry, like the curved value here, they're not going to give the same result. And then it makes a difference whether you take the approach of taking just the non-parametric empirical bootstrap, or whether you take the hypothesis testing approach of taking what you don't want as the null. Okay? So finally, we get to apply this to the problem at hand. So we recall that we got 96.5% confidence in the 910 clade in the original paper. So Efron works very hard to get the best possible null world and then do the analysis in that bootstrap world. And the result is 93.8% of the trees in his bootstrap do not contain the 910 clade. So the p-value is actually 1 minus that. It's the percentage of trees that do contain the 910 clade, and that's 0.062. Okay, so in some sense, we had 96.5% confidence, and now we have 93.8 confidence after all of our hard work. So the results are not that different. But if we happen to religiously believe in what we were taught in Stats 101, that 0.05 is the critical threshold, then the two results end on different sides of the 0.05 threshold, right? One minus the confidence here falls below 0.05, and here it falls above 0.05. So if we take this view, then the Felsenstein's conclusion is that we are confident in the clade, whereas the hypothesis testing approach tells us that we cannot reject that this clade is a coincidence and that we have confidence in the clade. Okay? Okay, so to summarize, obviously it's a very general and very flexible paradigm for doing statistical estimation and statistical inference. And it allows us to handle these complex situations with minimal assumptions and without doing complicated math. As a side note, if we try to prove theorems about the behavior of bootstrap estimates, it usually becomes very complicated very quickly. So actually doing theory on bootstrap is usually a very difficult exercise. But doing bootstrap is not a difficult exercise. And I think it has been very widely influential over the past few decades in science and industry, and I think with good reason. But I think, from my experience, is that the idea is often misunderstood and misapplied, and there's much more egregious examples than Felsenstein's example, which is arguably, it's debatable whether or not this is something that's appropriate. There are many examples where you see things really badly misapplied regarding bootstrap. And that's it. Thank you.